great pleasure to welcome you all to this talk by this lecture by Victor Lamme from Amsterdam. This is a joint meeting between the Academy and our Forum for Consciousness Research here in Oslo. And this lecture is being recorded and will be put online later on the website of our forum. And this is actually the first live meeting in quite a long time, since actually in this room we had the last meeting in December 2019 with Itzhak Fried standing here and talking about his concept cells, etc. Because of the pandemic we have had this long break, we had online meetings in the meantime and also another lecture in this room that was not directly in our forum. So it's a special pleasure for me to both invite and introduce Victor for this talk, because I think he's one of the most knowledgeable and original thinkers in this field. And he has launched this theory of recurrent processing that I think is combining several of the interesting features of other theories and also resolving some issues. We'll surely hear much more about that later. What I particularly like about your work is that it's very rooted in your experiments. You are doing experiments both in humans and monkeys, and so it's a strong empirical basis. And you are, as you know, a professor of cognitive neuroscience at the University of Amsterdam, and you have worked with both visual perception and attention and memory. And they say that you only to converge on the topic that truly fascinates you, that's consciousness. You are using a variety of techniques that we'll hear about, both single unit recordings and various imaging techniques in monkeys and humans. So previously I heard about other theories of consciousness also in this room. Stan Dahen and Jean-Pierre Changeux presented their global neuron workspace theory. It's one of the famous theories, and also Giulio Tononi in the literature who's presented his integrated information theory. And these famous and impressive theories have understandably drawn a lot of attention, but I think Victor's theory deserves also a lot of attention because, as I say, it combines a lot of the attractive features of these other theories and resolves some of the issues to a large extent. For instance, the question whether consciousness is seated in the front or the back of the brain, and the difference between excess consciousness versus phenomenal consciousness. So I think you'll hear more about. This is an earlier version of the theory. That is actually the first paper that I came across from you in 2006 in Transit Cognitive Sciences, towards the true neural stance on consciousness, which I really liked. We have published a number of excellent papers and an impressive citation index, so more than 20,000 citations. I will not have time to mention these papers, of course, but they are well worth looking into. And you're also featured in several interesting videos on YouTube, some of them very entertaining and even humorous, so I recommend them strongly. Then I, as usual, make a little advertisement for our forum. These are previous speakers in our forum, and we have an upcoming speaker later this spring. Actually, this is the wrong date, of course. This is going to be 19th of May 2022. Yair Pinto also worked with Victor Lamme about split brain. They come and talk then. But now I'm looking very much forward to your talk. What can brain science teach us about consciousness that we don't know already?
Thank you. Let me turn myself on. Yeah. Hi. Where's the remote? Yeah, the remote.
Just here.
So you hit it full.
I can close this one, I think that's...
Is this on? All right. Yeah, you mentioned it's recorded. Is it okay if I walk around a bit?
Yeah, I think so, yes.
Okay. Oh. All right. So, hi. I'm Victor from Holland. Can everybody hear me? Also in the back? Okay, great. Yeah. So I would like to talk about this. To give a brief insight in the title. Of course, consciousness is something which is very familiar to us. We know we lose it every night and then we wake up and we have it again. So it seems to be something that we know. But that's a thing I would like to challenge a bit. Maybe we don't really know what consciousness is, in the sense that we don't really even know what we are conscious of ourselves. I'll explain that, of course, but that's sort of the idea, at least the idea of the title. So, to introduce the topic, I would like you to view something that you have probably seen before, but nevertheless it's a way of introducing what I would like to talk about, which is this.
The monkey business illusion. Count how many times the players wearing white pass the ball. The correct answer is 16 passes. Did you spot the gorilla? For people who haven't seen or heard about a video like this before, about half missed the gorilla. If you knew about the gorilla, you probably saw it. But did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold. When you're looking for a gorilla, you often miss other unexpected events.
All right.
And that's the monkey business illusion. Learn.
Okay. Enough about that. So, yeah, as I said, you've probably seen this before, and then, or maybe this version not, or whatever. Anyhow, of course, this is the phenomenon that we call inattentional blindness. So you've not focused your attention on something, and therefore you miss it. You don't notice that the gorilla is appearing, or you don't notice one of the players leaving the game, or the curtain changing color. Inattentional blindness, it's called. Allegedly meaning you are blind to what's going on there. And of course that also implies you have no conscious sensation of what's going on there. That's the thing I would like to discuss a bit. But let's have a look at how we would be able to explain this. Well, of course the gorilla was on your retina, on your eyes, at least if you look this way. But somewhere between the eyes and, I don't know what we should call it, the blindness or the consciousness, the animal was lost. So where exactly did that happen? And what happens either in terms of neural processing in a situation like that, or what happens in terms of psychological stuff going on there? Those are the things I would like to discuss. So what's happening if you? So what's happening if something hits your retina and then goes to your visual brain, etc., etc. Well, one of the things that happens is what I call a fast feed-forward sweep. We make an eye movement about 3 times a second, and every time our eyes stop on the next image, this the information of this image is very rapidly transferred from early visual areas in the back of your head to more forward areas, temporal lobe, parietal. This is an image from monkey brains, and what you have here is the latencies at which information from a visual image on your retina arrives at those parts of the brain, earliest latencies. So as you can see, within something like 115 milliseconds, something that has hit your eyes is spread out all over the brain, more or less. And this is why we call this the fast, because it's pretty fast, feed-forward sweep. We call it feed-forward because it goes from these early low-level visual areas to higher-level visual areas in a what's then called feed-forward sense. And in monkeys, this takes about 120, 115 milliseconds. Human brains are bigger, of course, so that it takes a bit more time, like 200 milliseconds. And what happens during this feed-forward sweep is that all sorts of what we call visual features are detected. So these neurons in visual cortex, they detect shapes and orientations and colors and motion and all sorts of aspects of the visual scene are analyzed by these visual areas. But also more complex features like faces. For example, you have these face selective cells. You've not heard about those two in temporal cortex. These face selective cells are already active from these very first moments on during this feed-forward sweep. So, as I said, there's very basic tunings for things like orientation in areas like V1, V2, V4. These are all names that you can immediately forget, but it's motion detection, depth, color. This is what we call feature detection, and that's something very important that the visual system obviously does. And then there are these high-level categories or features, whatever you want to call them, detected also. So I mentioned faces, but for example in humans there's also what are called visual word form areas, so areas detecting that there are words out there, for example. But of course other things like, more complex shape, objects, maybe, and of course also things like emotions, gist, but that's not really all relevant now. But this is all done within these very few tens of milliseconds by the visual brain. And yeah, in that sense, this fast feed-forward sweep may provide what I call an intelligent sensory to motor reflex. Imagine you have to, I don't know, return a tennis ball that's served at you at like 100 miles an hour. Of course, if you want to do it correctly, you have to position your tennis racket in the right position. You have to analyze all the information of the motion and the position, your own position, all within, I don't know, a few tenths of a second. And this is typically something that you would need this kind of fast feed-forward processing for. Because we of course also have to realize that the brain is, I would say, sort of made, of course, to transform visual or other sensory input into some sort of useful output. Well, this is another sport illustrating the same thing. Now, there is quite general consensus that what happens during this fast feed-forward sweep is not at that moment accompanied by any conscious sensation of the visual input that has hit your retina yet. For example, this feature detection, like orientation, motion, color, etc., you can just as well record in animals that have been anesthetized. So even if you have an anesthetized animal, which, allegedly has no conscious sensations, you can still record all these cells doing their job. Same with face selective cells in higher level visual areas. You can also record these in anesthetized animals. For example, also this activation of these face-specific areas in the human brain. You may have heard of what's called the fusiform face area. That's a part of your brain which is constantly detecting is there a face out there, and there are a lot of faces out there now for me. But my FFA is very active. But you can also get this activated by stimuli that you don't see. And we'll talk a little bit more about that in a minute. But there's even activation of frontal parts of your brain, so the more cognitive modules, you might say, by stimuli that you don't consciously perceive. For example, because they are what is called masked. I will also talk a bit about that more in a minute. Now, after this feed-forward sweep, what you then get automatically, I mean, if nothing if nothing else happens, you sort of have to shoot the person to prevent this, I would say. It's what is called recurrent processing. Now, recurrent processing, yeah, well, by its name, implies that the information is no longer just flowing from, say, these visual areas to even higher visual areas and then to frontal lobe, but it's now also going in the opposite direction. That's what is then called feedback. Feedback connections, and so feedback connections going from higher areas back to lower areas. But there is also what are called horizontal connections within these cortical areas, which connect cells which are initially not connected. And what these kinds of connections enable is, well, what is then called recurrent processing, implying that these cells now start to talk to each other way more than they did before. And there's two versions of this. One we call local recurrent processing, say confined to just visual areas, so there's just visual areas talking to each other. And then there is more global recurrent processing, which is recurrent processing, well, you could say throughout the whole brain, also involving these more frontal parts of the brain, and what have you. All right, so interesting question then, of course, is, yeah, well, why would you need this if you can do such intelligent stuff with this feed-forward sweep? First, let me show you what these recurrent connections actually do in terms of, you know, what happens to these neurons that you may record from in, for example, this primary visual cortex. And that's what you have here. So this is monkey V1, as it's called, primary visual cortex. If you stick an electrode in there, which is something I did a long time ago, and you know, for ages, but primary visual cortex is the very first area in the brain where visual information is entering the brain. And there you have very small, what are called receptive fields. So each neuron is only looking at a very tiny piece of the visual world, something of the size of the nail of your thumb. And what you then can do is present visual stimuli within this receptive field. That's the classic way of doing electrophysiology. And then, for example, you can show these kinds of line segments in that receptive field, and if they are of the proper orientation and stuff, these cells will become activated by that. Now, but what you can also do is then give these line segments different contexts, like shown here. So, within the receptive field, this is what's happening, but these line segments apparently perceptually belong to such a homogeneous texture background, you could say, or you could have the same line segments but now belong to such a figure. And then you can nicely, I would say, isolate this feed-forward activation from this recurrent activation as shown here. And so what you have here are the response of a bunch of neurons to these kinds of stimuli. So again, so this is the figure response, as we call it, and this would be the background stimulus. And as you can see, up to something like 100 milliseconds, the neuron responds exactly the same to such a stimulus as it does to such a stimulus, indicating that indeed this neuron is only looking at what happens within the receptive field. And as that is the exact same, well, it also responds the exact same. And this is typically a hallmark of this feed-forward activation, neurons looking at, you know, through a very small tunnel, what we call the receptive field, and not caring about anything else. But then after the 100 milliseconds, you will see that the response to this stimulus will be larger, as shown here, compared to this one. So after this 100 milliseconds, these neurons now start to care about, you know, what the more global context is of these small line segments that they are looking at. And then they give a stronger response for this situation compared to this one. Yeah, feed-forward sweep, 40 to 100 milliseconds, and then from 100 milliseconds onwards, you get this phenomenon that we call contextual modulation, because the neuron's responses is modulated by the perceptual context. Now, if you record from neurons all along this line, so receptive fields all along these positions, what you will see is that this elevation of the response, which is isolated here, happens all over the figure. That's also shown here, by the way, in a different way. So you have the receptive field of the neuron in different positions relative to the figure, to such a figure. And then you see that as soon as the figure hits the receptive field, you get this elevated response. It starts a bit earlier here at the boundaries, which is maybe interesting, but not something I want to talk about now. But So in that sense, it really also reflects this, well, you sort of reflects this percept you have of this figure overlying the background. Figure overlying the background is sort of reflected by the neural activation of the figure cells being higher than activation of the background cells. But as you can see, initially it's uniform, and so cells don't care about global context, but after a while they do. Now, interesting thing is that if you take away higher level visual areas, so areas, well, what are called extrastriate areas, so areas beyond primary visual cortex, then you still find these neurons responding, etc., but you selectively lose this modulation, as is shown here. You still have the thingy on the boundary, there's a different reason for that, but the figure ground modulation, the contextual modulation as we call it, is abolished if you take away these feedback, the possibility of higher level visual areas to send feedback signals to primary visual cortex, which is of course an indication that indeed this contextual modulation is mediated by these feedback connections. So what this means, sort of, is that if you show a stimulus like this, what you first have is that indeed at the latency of something like 50 milliseconds, here in early visual cortex, primary visual cortex, you have these what we call low-level feature detectors, which are detecting the orientations of these line segments and stuff. And then this information is transferred to higher visual areas, shown here in temporal lobe, parietal lobe, also occipital lobe, of course. Where we have cells that are able to detect more complex shapes and stuff like that. And then at some point these neurons start to engage in these feedback recurrent connections, and then all this information is sort of combined so that you have this figure ground percept. That's the idea at least. Interesting thing about these feedback connections, by the way, is that they use different types of, at least to some extent, different types of neurotransmitters. We've shown that by blocking these neurotransmitters. For example, blocking they don't use different neurotransmitters, different receptors, sorry. At the NMDA receptor, if you block that with a drug we call APV, then you will see that this, well, more or less selectively disrupts this feedback processing signal again, so the recurrent processing. You have a quantification of that here. Also a little bit of the feed-forward sweep, but way less. Whereas if we block the AMPA receptor, which is a different receptor, so it's a different synaptic receptor, with the blocker we call CNQX, then we don't so much interfere with the recurrent processing, but interfere much more with the feed-forward signal. So that already indicates that there are some differences in how these feed-forward connections work and how these feedback connections work. But that difference becomes most obvious if we anesthetize the animal. If we anesthetize the animal, something very striking happens, which is what you see here. So here again you have the situation in the awake animal. I didn't mention it, but the recordings I just showed you were all done in awake monkeys. So these were monkeys that were trained to look at a stimulus monitor, and then, well, they had implanted electrodes in their brains, and then they had to look at these stimuli, sometimes also do a task. But anyhow, these were monkeys that were awake. But if we then recorded from the very same monkeys, with the very same implanted electrodes, but now while anesthetized, you suddenly get this result, which is no modulation, no contextual modulation at all, as you can see. This is a structure for motion stimulus, as we call it. It's sort of similar to the thing you saw with the oriented line segments, but now there's motion, which is generating a figure ground percept. So what you have here in the anesthetized condition is that you still get the feed-forward activation. You still get these cells which are looking at the orientations and motions within the receptive field, but they don't care about the visual context anymore. They're not modulated by whether it's figure or background or anything. They just look at what happens within the receptive field. They're just the activity is only mediated by this feed-forward activation, and that's of course a very interesting finding, because it implies that these feedback connections are way more susceptible to anesthesia, but it may also imply something different, which is that these feedback connections, because they are abolished by anesthesia, maybe much more important for you having a conscious sensation, or you being conscious in this case, than the feed-forward connections. So the feed-forward connections are still there in the anesthetized case, and yeah, well, you have to assume that also these animals do not have conscious sensations while anesthetized. At least that's what we hope, of course. And yeah, implying that feed-forward connections in themselves are not related to having conscious sensations. And we did lots of other experiments following this to also prove that point, but now again in awake monkeys. So one way, of course, of making visual stimuli invisible is by a technique we call masking. Masking is a very simple technique. We just present the visual stimulus and then you present another one briefly after it. Usually one which is sort of similar or something like that. And the effect of that is that you don't see the first one anymore. Just presenting the first one very briefly is not so much interfering with you consciously perceiving it. I mean, you can present stimuli very briefly and you will still be able to see them, but if you present the stimulus briefly and then present another one after that, you don't see the first one anymore. That's why it's called masking. And typical intervals over which this work is, for example, an interval of something like 40 milliseconds between the first one and the second one. So yeah, it's fairly brief, all this stuff. But what you have there is then that if you present stimuli and then mask them with varying intervals between the stimulus and the mask, that's what you have here. This is expressed in monitor frames, and this is from the old days when we have CRT monitors, so it's 16 milliseconds per monitor frame, the old days. So 4 monitor frames would be 4 times 16, 64 milliseconds. Up to that point, you don't get any of these modulation. You don't get any of the modulation anymore. So that's what you have here. The difference between figure and ground again. You don't get that. You don't get that for these short SOAs. And these are that's what these bars reflect, the amount of modulation you get. You only get that for these longer delays. And these are exactly the delays where the animal either doesn't see the stimuli or does see the stimuli. In this case, the animal had to indicate whether it saw the stimulus by making an eye movement to it, for example. And so, again, sort of the same result in the sense that if animals don't, now they are awake, but if they don't see the stimulus, you don't get the modulation, and if they do see the stimulus, you do get the modulation. While in all these instances, regardless of what they're seeing, you get this feed-forward activation, as you can see. Now we sort of try to challenge this a bit more by having animals just look at these kinds of stimuli and then wait for them to spontaneously either see the stimuli or not. No masking, nothing. Because of course it can happen that you just look at the stimulus and then, yeah, for some reason you don't see it. Now, how do we ask animals whether they see something or not? Well, you can have them make saccadic eye movement, but it's more interesting to also give them the opportunity to really positively indicate, well, I didn't see anything here. So how did we do that? We had them, again, we showed them these kinds of figure ground stimuli again. These figures could have different positions, so 3 different positions. And then whenever they saw the stimulus, they had to make a saccadic eye movement, so an eye movement to the stimulus to indicate to us, oh yeah, I saw it, and it sits over there. But they also had the opportunity to say, no, I didn't see anything here, because we also presented what are called catch trials, which would be a screen like this, but without any figure at all. And they were trained on those trials to maintain fixation, to indicate to us, well, there was no stimulus here. So, and they were perfectly fine in doing that, so they made eye movements to these figures, and they maintained fixation when there was no figure. But it also sometimes, in something like 8% or so of the trials, happened that there was a figure presented, but they still maintained fixation, as if indicating to us, wow, I didn't see any figure here. And then if you look at the, and this is something about latencies of eye movement and stuff, you can forget about that, but something very striking happens, and that's whenever the monkey was making the eye movement indicating, well, I saw the stimulus here. Again, you got the modulation that I showed you before, but when the monkeys maintain fixation, indicating, well, didn't see the thing here, all the modulation is gone. It's a bit like the anesthesia result, but now in an awake monkey. And so it's like the animal is sort of temporarily, at least as you could say, unable to see the figure. Still, you get the feed-forward activation, but the feedback modulation you selectively lose. Very selective effects like this. So yeah, just to summarize this, so this is the anesthesia result, now in a different format. This is the masking result, the figure ground result. So in all these instances where you don't have feedback modulation, you don't have conscious percepts, and the other way around. While also in all these instances, you have feed-forward activation, regardless of whether there's conscious sensations or not. Now, we also took this to human experiments, so this is from an experiment in human subjects. Of course, I already explained, in human subjects you have this conveniency that there is what's called the fusion from phase area, which is an area which is selectively activated by phases. And we masked these phases with a different technique, which is called dichoptic masking. Not really all that important to get into these details, but the consequence again is that, yeah, people didn't see the stimuli. But regardless of people seeing these stimuli or not, in both cases you still get activation of this FFA, which is actually quite a surprising thing. So even if you don't see a phase, if there is a phase somehow there, your FFA is detecting that phase, which is interesting, I would say. But of course that begs the question, okay, well, what's the difference then between what's going on when you see the phase or when you don't see the phase? Well, that's what you have here. This is EEG responses, whereas this is functional MRI. But in the EEG you can very clearly see the difference between the invisible and the visible phases. The invisible phases evoke a brief blip of activation, again this feed-forward type of activation, and you can see it here in the back of the head, lasting between 82 or 125 milliseconds, but the visible phases evoke much longer, more prolonged activation. It's a bit like the results I showed you with the animals, the monkeys, the modulation effect. But now, yeah, in the EEG. And if you take that to the fMRI back again, and then you analyze to what extent there are interactions between different parts of the brain, you see that the visible phases selectively evoke interactions between the fused-form phase area and these earlier visual areas which are detecting shape, orientation, color, motion and stuff. So that's really seems to be the hallmark of you seeing something, that there are these neurons in, say, fused-form phase area engaging in interactions with all sorts of other visual areas to really make you see the face as the face, which sort of makes sense. Because seeing a face is, of course, much more than you knowing that it's a face versus, I don't know, a chair. Seeing a face, of course, also entails that you see the color of that face, the shape of that face, maybe the emotion that's on that face. It's an integrated percept, as we call it, and that's, well, apparently directly reflected in the fact that you have these interactions which are making that. So this is, as Johan already said, I just did these experiments, never thinking about anything theoretical or something, but out of these experiments, yeah, it sort of automatically followed, well, apparently there's something special about these recurrent interactions in consciousness, so, yeah, well, why not call it a theory? It's just, I mean, it's not, I'm not a big theorist or something, it's just something, yeah, it's more like a set of empirical findings than a theory, I would say. But anyhow, I found it quite striking that this feed-forward activation really is not accompanied by any conscious sensations, whereas with recurrent processing is. And that's basically what there is to this whole recurrent processing theory, aside from a few other things which I will mention. Now, of course, what I showed you here are all interactions between areas in the brain, in the visual brain. But I also told you that there are these more global recurrent processes going on. And so that after what's going on here, which typically starts from, well, in human brains, starts from something like 200 milliseconds, there's of course also this more widespread recurrent processing. And as Johan mentioned, you've already, I don't know whether you were there, but there was this talk by Stan de Haan, I guess, about global workspace theory. And of course, global workspace theory has the position that, well, this is all fine, these recurrent interactions in the visual cortex, but you need the involvement of these frontal areas to really have a conscious sensation. No one knows exactly why, but that's the idea there, of course. And so only when you have what they call global ignition, consciousness starts. And what they propose, global neuronal workspace theory proposes, is that this is something we should call pre-conscious. Let me explain this a bit. So yeah, I'm not going to go into all the details of global neuronal workspace theory, of course, but they make a distinction between, well, sort of similar to what I would say, subliminal stuff, which is, you know, some activation in, say, visual cortex, which is not penetrating very deeply, not going very far in terms of feed-forward processing. And then you have pre-conscious processing, which is indeed interesting stuff going on in visual cortex, maybe also oriented connections going on there, but they call that pre-conscious. And then things that only get conscious if you attend to them, if it's processed by frontal cortex, because that enables what they call access. I'm no expert to explain really what that means, but it's something in the order of, well, I don't know, you knowing that stuff is out there, I guess, or that you can, what they call cognitively manipulate the visual information, stuff like that. So then you really, well, have what they would consider consciousness for the visual stuff that's processed in the back of the head. Yeah, so and they have all these experiments, you know, for example, attentional blink paradigms. So you present a visual stimulus, in this case a few letters, by the way, so it's not all the visual, but it's a letter stimulus, and then you present the second one a few hundred milliseconds later, and then typically what would happen is that you don't notice the second one. Because, again, your attention is diverted by the first one. That's why this is called attentional blink. And then what they observe is that only when you notice this second one, you get this activation of these frontal parts of the brain. And when you don't notice it, you don't. So they take this as evidence that indeed, you know, frontal activation is the correlate of you really seeing the second stimulus, which makes sense. Okay, I would say. But of course it depends on what you mean by seeing, as I will elucidate in a minute. So, but anyhow, what this means is that there is, yeah, you could say some controversy about where the magic happens, as I call it. The magic being, well, you know, visual information going from stuff in the dark, how should we call this, to visual information being in your conscious mind. Somewhere this happens, and as I've talked about in the introduction with the gorilla, somewhere it's in your mind, and at some point it's not. So where exactly does that kind of magic happen? Well, as I said, recurrent processing theory would say, well, this is where the magic happens. And of course, global neuronal workspace theory would say, oh no, wait a second, this is all fine, but this is only pre-conscious, this is where the magic happens. Well, who's right? That's of course the question then. This also relates to something else, which is a more theoretical point, which is that if we want to find what's called true NCC being the neural correlate of consciousness, so what's exactly the point in the brain where stuff gets conscious, we have to take care that we don't jump to conclusions. For example, that we don't consider processes that follow conscious experience as part of the NCC. And so that would, for example, be, you know, if I'm in a task where I have to push a button whenever I see something and push a different button whenever I don't see something, well, of course, me pushing this button or me pushing this button will activate different muscles. And those would be different consequences of me seeing seeing the stimulus or not. But of course, it would be a bit silly to then say, well, this is the consciousness muscle, because, you know, it's a consequence. And of course, that also holds for motor cortex and stuff, and you can even place it more back, and maybe even, well, also all sorts of things which are following the conscious experience itself. Of course, that's not what we're interested in. We're interested in neural stuff that's really turning the light on, you could say. But of course, there's also stuff preceding conscious experience. For example, you know, when I see you, well, there's stuff going on in my eye. Well, I'm pretty sure that if I would take out my eye and put it on a table, it would no longer have conscious sensations. We don't know actually, but we have sort of assumed that. So that, and of course, yeah, what recurrent processing theory would hold is that, well, this would be feed forward and this would be visual local recurrent processing, whereas of course, and then recurrent processing theory would say, well, all this frontal activation is actually something which comes after the conscious percept being generated, for example, because you have to push buttons, you have access, you have attention and stuff like that. Whereas of course global workspace theory would say the opposite. They would say, well, local recurrent processing, so stuff only happening in visual cortex, is something which is preceding conscious experience, and only this would be true. This would be frontal cortex activation, and that would be the true NCC. That sort of, and then this would be something even following that. So I don't know, your muscles. All right, yeah. So how to deal with that? Of course, that's a very difficult that's a very difficult discussion actually, and that's also more or less where the discussion sits now. You know, what should be believed there? Almost a matter of taste, I would say. There has been some efforts to tackle these issues, for example, with what are called no-report paradigms. So that's paradigms where you have subjects looking at visual stimuli, and then yeah, you wonder, are they seeing the stimulus or not, or are they seeing one stimulus or the other one, which you can get, for example, with a technique that's called binocular rivalry. So you present this to the other one eye and this to the other eye, and if you do that, what you have is that sometimes you see the green one, sometimes you see the red one, and sort of spontaneously switches. And of course, it's interesting to see, you know, what happens in the brain when you see this or when you see this. Now, of course, if you want to know what people are seeing, so whether they're seeing this or this, you normally would have to push buttons. But what they do here is have not people pushing buttons, but just look at how their eyes move. Because if this thing is moving to the right, what your eye will do is follow the stimulus and then move back again, follow the stimulus, move back in again. This is what we call optokinetic nystagmus, OKN. And by means of that, you can sort of know, without the subject pushing buttons or even saying anything, know whether someone is seeing this one or is seeing this one. And if you do that, and compare that to the situation where people are pushing buttons, indeed you get a very striking result, which is that the pushing buttons, indeed, from the pushing buttons, indeed you get activation of these frontal areas, so global workspace, you could say. Whereas if people don't push buttons anymore, and you just look at the OKN, the eye movements, you don't get the frontal activation anymore. Well, that was considered an important result in, you know, showing that indeed frontal activation is a consequence of consciousness and not so much consciousness itself. Well, then there has been a recent experiment, this time in monkeys, where they did the very same thing basically, and then they showed, no, wait a second, you also get frontal activation. You can even decode from activation in frontal cortex whether the monkey is seeing either this or that. So, you know, it's sort of going back and forth, of course, these kinds of arguments. So I've once written that indeed this discussion about where the magic happens is sort of in a stalemate. If you play chess, you may know what I mean. But it's going back and forth a bit, and it also seems to be a bit of a problem, like that we seem to be explaining, or trying to explain different things, I would say. All right, so and in that sense, it's also, this discussion is also going on with respect to different theories of consciousness. So, for example, integrated information theory. Well, as of lately, it has sort of positioned itself on the back of the head camp, in the sense that it indeed identifies what they call a posterior hot zone. It's a very nice marketing term, of course, where they consider the back of the head ideally suited to generate these high integrated information states. So they're in the back of the head camp, and then there's higher order thought theory, different theory, which is also quite prominent, which is again in the front of the head. Don't have time to discuss all that, but it's basically, you know, higher order thoughts that it in itself already implies that it's, well, higher order thoughts. So that's a pretty frontal theory as well. So there are these two camps, you might say, indeed, of, you know, frontal, back of the head, front of the head. So where is this going? Maybe we should just stop talking about consciousness and just, you know, call the things by the experimental paradigms that are often used. Because if we look at for example, the things I talked about, masking and stuff like that, that's typically in the domain of making things either invisible or visible, where of course the global workspace people tend to work with attentional paradigms, where, for example, things are not reported because the attention is diverted, just like in the gorilla thing or stuff like that. I don't find that satisfactory because, you know, I don't care about attention. It's actually a topic I hate. Yeah, visible, invisible, that's very nice, but that's not why I'm doing this. I really want to know how it's possible that with 1.5 kilograms of fat and protein in your head, you have these conscious sensations. That's, you know, that's the mystery, I would say. That's the magic I would like to explain. So I want to keep on keep on fighting with this. So yeah, so how do we deal with that? Well, I said that I would also mention a bit of psychology. Let's get to that now. You said with this another phenomenon that you've mentioned before. It's funny.
In this experiment, a subject comes up to a counter and a first experimenter hands them a consent form. As soon as they finish signing the consent form, they hand it back to the first experimenter, who then takes the consent form, ducks down behind the counter to put it away, and a different experimenter then stands up and hands the subject a packet of information and sends them into a hallway where we ask them questions about it.
The lady who took me up here, she opened the door for me and told me to walk over to the desk. I think there was a sign that said experiment.
Mm-hmm.
And a man there gave me a form to sign.
Mm-hmm. Did you notice anything unusual at all after you signed the consent form?
I just signed it, and I didn't even pay attention to anything that was written on it.
Okay.
Yeah.
After you handed it back to him, did you notice anything unusual happen at all?
No, I probably wasn't even looking that direction. I probably
Okay.
turned and looked towards the clear door. I saw some people there.
Okay.
Then I turned back and looked at him for a second.
Okay. Did you notice anything unusual at all after you signed the consent form?
No.
This is only going to take 5-10 minutes.
Yeah, it'll be real short.
Okay.
A different person actually stood up and handed you this form and sent you out toward me. I gather from your reaction you didn't notice that?
No.
Okay. Don't feel bad about that. Actually, most of the time, we find about 75% of people don't notice.
You serious?
Yeah. The person who stood up with the packet was actually a different person
Wow.
than the first person.
That is incredible.
So I gather you didn't see it.
I didn't catch that, no.
Okay. What's really interesting is that some people notice these changes and other people don't notice these changes.
Okay, if you could just take this.
And we really don't yet have a good idea what separates those people who don't from those people who do. It might be that there are individual differences and some people are better able to detect these sorts of changes. But it's also possible that it's just coincidence, that the people who noticed it just happened to be focusing on a feature that changed.
Yeah, so this is another well-known phenomenon which we call change blindness. Again, they have that word, blindness. But of course, yeah, it's sort of strange in the sense that you're looking at the person and then, you know, the person is ducking behind the counter and then the different one stands up. Did you really not see that person, that first person? What's going on there? So it's sort of the same thing, of course, as with the gorilla, but on a different domain. So yeah, and we did a lot of experiments on this change blindness phenomenon to sort of get a grip on, you know, what's exactly going on there. So yeah, so this is the idea. Yeah? So we have these two people changing, and of course this is a boy and this is a boy. Maybe for the girl that you saw in the end, this was a boy, and this was a boy and this was a boy. So you know. Maybe that's why she noticed the change, but anyhow, so this guy didn't notice any change, and then so this is Daniel Simon's asking, no, well, he didn't. So happens here. Now, the different ways of interpreting this, and the classic way of interpreting this is, what, for example, Daniel Dennett would do, and what of course also global workspace people would do. Well, if you didn't see the change, well, you didn't have any conscious sensation of that person. That's, yeah, sort of logical conclusion, I would say. Case closed. But of course, yeah, the intuition that people have is sort of different, you know. Well, I didn't notice the change, but did I really not see that person? Sounds a bit strange to me. Well, some people have argued, like for example Michael Cohen, that's this guy. Yeah, well, you sort of have an idea of a person standing there, but this is what we call the gist of a person. So it's not really that you saw the person, just something, yeah, it was a person, but you didn't really have a conscious sensation of the full person or something like that, but just of the gist of the person. So, okay, so let's delve into these issues. Yeah, so this is me and this is me, etc. So anyhow, yeah, this is from another presentation where I used this kind of format. But anyhow, we did these kinds of experiments where we tried to get a grip on these change blindness phenomena. Again, well, not by using these movie things and these interesting life experiments, of course, but by showing people arrays of objects like this. So there are 8 objects. We show the array of objects, then there's a blank interval, you know, just like the person ducking behind the counter. And then we show the objects again, but now one of them has changed, and we even point to the one that may or may not have changed. And of course, in this case, it has changed, but in the other 50% of cases, it didn't change. And then people simply have to answer the question, well, did it change or did it not change? And just as you saw in the video clip, people are really awful at that. They're only like 60% correct, which is slightly above chance level, which is 50%. And what you can do is convert this percentage correct via formula into a capacity that people have for monitoring these changes. So out of these 8 objects, how many do they monitor, you could say, for change? And given that the 60% correct, that calculates to a capacity of 2 objects. So allegedly implying they only really have a conscious, knowledgeable sensation of 2 of them at a time, not all the 8. Because if they would see all the 8, you would say, the argument would go, well, then they would always notice a change and they would be 100% correct. So that suggests, just like the change people would like you to believe, is that conscious vision is actually very poor. You think you see all these 8 objects, but in fact you only see 2 of them, because that's where you focus your attention and stuff. It's also called the refrigerator light illusion. And so it's the same as when you open your fridge. Of course, the light is on then, and then you may think, well, the light's always on. But yeah, it's off when you close it, but you don't see that. So that's why this is called the fridge light illusion. Because, of course, every time you look at any of these objects, you focus your attention on any of these objects, you see them. And this gives you the illusion that you see them all, but you only see 2 of them. At least that's the take that these illusionist people have on this phenomenon. And it's in that sense the same as with the gorilla. And so, yeah, you don't see the gorilla even only if you focus your attention on it, you actually see it. All right. However, we did a slight variation of these experiments where we didn't present the cue here when the second array was presented, but we presented the cue during the interval. So we showed people these arrays of 8 objects, and then, say, 1.5 seconds or so later, we presented this cue, and then showed the second one. And it made a huge difference, because now suddenly people were very good, well, it's much better at this task, and if you converted the percentage correct into capacity, you got something like 6 or 6.5 or 5 or 4, depends a bit on the delay. But anyhow, much larger than this 2 that you find initially. So that implies the following. When you show this array, and then it disappears, you can still point at a position in space, and then people can sort of retrieve what was over there. Oh yeah, there was a, there was a motorcycle there. And if you then present the second array, people know, oh well, now it's a frog. And then it's easy. This is also introspectively what you have if you do these kinds of experiments. You show this array, and then a few seconds later even, you show the cue, and then you know what was sitting there. The only thing that happens is that as soon as you present this second array, this representation in your head that you had of these all 8 objects is overwritten, is disappearing. So that gives a very different image of visual perception, or at least the representation that sits inside your head, which is that it's actually very rich. It's containing many of these objects, maybe all of them, or at least quite a few. And that the real problem with change blindness is not that you didn't see that guy that was standing there in front of you. The only thing is that if he ducks behind the counter and then comes up again, this guy is now overwritten, you could say, by the new one. You forgot about the first guy. So it's more change amnesia, you could say. Now, we've done some experiments to see to what extent these different capacities depend on different parts of the brain. I'll go over this very quickly. We did some TMS experiments where you can inactivate parts of the brain, in this case inactivate prefrontal cortex, for example, and then you can see that this affects this working memory capacity, as we call it. So that's this one, so the stable one, which is not interfered by the second one. By the way, this is so. Let me get back a bit. And so whenever you have the idea we have about what's going on here is you see a scene like this, then you have this fragile representation of almost the whole scene, and then you have this stable representation of these two objects. And these two objects are not overwritten by a new scene because they're stored in frontal parts of your brain. And that's exactly what we find here. So if you inactivate frontal cortex, this low capacity representation, the working memory representation is lowered a bit. That's typical for TMS experiments. Whereas the other one is not. So the purely non-mnemonic visual representation is not interfered by inactivating dorsolateral prefrontal cortex. Also, if you manipulate attention, so here subjects have to do a foveal letter task, and then at the same time do this change detection in the background. Fairly difficult, but people can do that. Then you can see that if they have to attend to these letter tasks, you will find that this low capacity representation is interfered with, but the high capacity representation is not. So indicating that this representation is indeed about attention, about dorsolateral prefrontal cortex, and that this one is not bothered, you could say, by attention. It's more bothered by something visual in the sense that the capacity you have of storing all these objects depends on your visual cortex size, it depends on glutamate concentration in visual cortex. You can even booster or inhibit the size, the iconic memory size, so this is how much more items you can store in fragile or iconic memory. When you apply what's called TDCS, that's basically putting a battery on your head, then you can increase the capacity a bit, or decrease it depending on the polarity. Anyhow, that's, so what this all means is the following. Sorry to go over this a bit quickly, but you see a stimulus like this, and then you have a visual, rich, large capacity representation of that visual stimulus in your head. That's however easily overwritten, and whenever there's a new scene, this is gone. There's new stuff represented in the visual cortex. It's depending on visual cortex, on each of these things I showed you. And then in frontal cortex, at the same time, you have this small subset of these objects, which is in working memory, which is small capacity, which is stable, but which depends on where you attend. Now, again, some people, as I said, have argued, well, it may seem that you see that you have this large capacity representation of all these 8 objects, like shown here, but it's not really a detailed representation. It's just something a bit vague. So we try to counter that by doing these kinds of experiments where we ask subjects not only to detect such changes, but also to indicate, okay, so this changed, so this frog is no longer something that was there before, but what exactly was the thing that was there before? So was it either this, and this? And then whenever they are that correct, we call that a high quality representation, and whenever that was incorrect, we call it a low quality representation. And as you can see, actually this high capacity fragile memory representation is almost all consisting of these high quality representations. So people really know when you present the cue here, oh, there was a motorcycle there, oh, there was a butterfly there. And there's one low quality in all of these, also in the working memory one. So it's a fairly detailed representation. We also ask subjects to indicate the exact orientation of such an arrow, and then the same thing, indicating that it's a very precise representation as well. This is a particularly nice one because what we've done here is that we also try to find out to what extent this representation really is a perceptual representation, which is of course going at the heart of the question as to whether this is a conscious representation. So we presented these kinds of what are called Canissa inducers, and you may know these from what's called the Canissa illusion. So if you orient these Canissa inducers, these Pac-Man figures, in the right way, you can see this as a arrow, as a triangle, in this case pointing up. And of course that means that if you do that, if you have this perceptual interpretation of these 4 items, you can now suddenly reduce the 4 items to a single one, which is an arrow pointing either up or down or whatever you. So that's what you see here. And of course, if you don't do that, if you don't have the kinetic configuration, well, you can imagine that it becomes very, very difficult to monitor these, what are they, 8 times 4, 32 Pac-Man for any change. Whereas if you have the perceptual interpretation, you only have to monitor 8 of them. And then you can look again at, cues at different positions, and that's what you have here. So there's a huge difference for the kinetic versus the control condition, but that difference is there not only for the working memory representation, but also for fragile and iconic memory representations. So it's a really perceptual representation that's sitting out there of these 8 objects. That's basically the idea here. So these visual representations, which are not depending on attention, which are not about access and which are not about report. So basically you could say the gorilla that's out there, you have a perceptual representation of the gorilla. You just forget about it, basically. At least in these, so it's not a gist, nothing like that. It's really detailed. That's basically it. And this amounts to what we call the overflow argument, or at least that's a thing that NetBlock has called it. Overflow argument being that actually we have a very rich and detailed visual percept, but a detailed and rich visual percept is much richer and more detailed than you can ever store in working memory, report about, talk about, push buttons about, have access about, and stuff. And so that's what we call this the overflow. Perception overflows cognition, it's called. That we consciously see much more than we can intend, memorize, or report. That's basically the idea there. Now then still, of course, there's this never-ending argument. Yeah, that's all fine, but why not call this pre-conscious and this conscious? So, of course, you can, as I said, you can discuss these things like till your socks wear off. Well, I think the real, thing to judge these things by is that, of course, taxonomy matters. I mean, as I said, it's important to know how the 1.5 kilograms of fat gives you these conscious sensations. So in that sense, we shouldn't just go about this lightly. And I think one of the main arguments about whether we should call either the one or the other one the conscious representation is whether the neural processes that underlie these different representations explain something about your conscious sensations. Now, what's there to explain about conscious sensations? Well, an important thing to explain about conscious sensations, I already mentioned this, is that if you have a conscious sensation of, say, a face, it's not just, you have your face module, which is doing face stuff, you have your orientations, you have your colors being represented, you have your motion being represented. Of course, the typical, I would say the most important feature of conscious sensations, and this is something that, of course, is also argued by integrated information theory, is that this is all integrated into one single, unified, coherent percept. And that's, I think, what we would like to, one of the major things we would like to explain about having conscious sensations. And of course, that's fully explained by these visual interactions, neuronal interactions in the visual cortex itself. I mean, what else would you need to have that kind of integration of visual stuff? I really don't see how anything frontal or how attention or how reportability or how access would add anything to that, apart from that it adds, reportability, access, etc. And so, and of course that also links to this whole thing which we already know for decades, which is that perception typically is what's called cognitively impenetrable. And so it's sort of impossible to not see the kinetic triangle here. These are even more striking examples. Even if I tell you that this is the exact same, the exact same the exact same wavelength coming from this compared to this, we cannot help seeing this as a different color compared to this one. Same with these two. And so these are again the exact same brightness levels, but we cannot help seeing this as darker than this. So in that sense, cognition, as it's called, knowing stuff, doesn't make you see things differently, which is called cognitive impenetrability. But it's very much related to that too. And if we map these kinds of visual functions on neural processes, and so we have all these visual processes where you have information being detected on very tiny parts of the visual field. That's typically done by this feed-forward sweep. But as you start to look at all these visual processes where you integrate all this information into a coherent percept, that's typically something that's done by recurrent processing in visual cortex itself. So I think this is I genuinely think that this is a better way to do justice to this search for the neural correlate of consciousness, because it really explains, why consciousness looks the way it does. And I generally don't think that anything frontal explains anything about that. And yeah, this is another bit more theoretical point, which is that, of course, by looking at feed forward versus recurrent processing on this axis and depth of processing on this axis, you can also give consciousness an independent ontological status, which is sort of a philosophical point, but it means that in this case, this is the unconscious versus conscious axis, which is feed forward versus recurrent, and this is the cognition axis, so intended, attended, so stuff like that. So you also see how it's then different. So yeah, those are my arguments, I would say, to say, well, there are basically two different kinds of magic happening here. The first one being that, if you go from this feed-forward isolated modules doing their visual stuff to this recurrent processes in visual cortex, that's where you go from dark to seeing, you could say. And this is where you go from seeing to knowing what you see, implying that you remember it, that you can report it, that you can push buttons, etc. But that, of course, has a very important implication, which is that if indeed you are looking at such a person and then there's the next one standing up and you didn't notice the change, you still had a conscious sensation of that first one, and of course also the second one. You just forget about it. Consciousness has, limited memory. Conscious perception has limited memory. That's the problem there. Change blindness is not a failure of conscious perception. Change blindness is a failure of attention, memory, cognition. And that's sort of, if you want to go back to the title of the talk, I think this is really what these kinds of experiments tell you about conscious sensation. Well, that you may not have known before, in the sense that it's sort of compelling that indeed, if you look at such a scene where there's this gorilla passing by that you don't see, indeed it seems like you didn't see the gorilla. But what this implies is that actually you did see the gorilla. You just forget about it. That's basically it. And so, there's lots of stuff here. But so, point being, if you look at such a scene, there's recurrent processing of the boy, also this one. So, that implies that you have conscious sensations. And it's, of course, also very much linked to this idea of integrated information theory. And by the way, finally, this is, of course, also a way of judging, you could say, whether there's consciousness in other beings than us. So this is, of course, an important other question. I recently wrote a paper about that. That's why I mentioned it. This often, by the way, non-linear transition from this more modular and feed-forward activation to more integrated recurrent activity is quite ubiquitous in the animal kingdom. It's basically everywhere. For example, in flies, there's interesting experiments there, where you also have this difference between feed-forward and feedback activation. And it's striking that you get the very same result. That if you anesthetize the fly, you also more strongly inactivate the feedback connections compared to the feed-forward connections. And this is a fly. And therefore, I think that also flies have conscious sensations. Of course, they're very different from our conscious sensations, but they matter to the fly, I would say. Not that I don't kill flies. I kill flies. That's the point. I also eat meat and stuff. So, flies also have this difference between being in the dark and having a conscious sensation. And they also wake up in the morning, by the way. So this is mentioned in those papers. So thank you very much. Sorry I'm a bit too late, but thank you.
Thanks a lot, Victor, for a great talk. You want to take some questions now? We also have coffee served, and then after 10 minutes we can come back and have more discussion.
Fine.
what do you prefer? Do we want to take some immediate questions, or should we get back?
Well, there were very urgent questions about, I don't know, flies, monkeys, or whatever, and of course, I'm happy to answer them, but if people want to have coffee, I can totally understand that too. So whatever they like. Coffee?
Okay, we can go for coffee and then come back in 10 minutes or